having derived this formula, now let's go ahead and use it, okay? So, first of all, I want to be very clear, this answer, this sum is only good for items that have this form. So if I've got like 1 over n squared, whatever, I can't use it. It has to be a geometric series. It has to be some number to the power of n's. Okay? So, but once I have something of this form, I can just go ahead and use it. I'm like, okay, what is that? 4 times e over pi to the n minus 1. So if I look at this, a is 4, and e over pi is my r, okay? And the question is e over pi less than 1 or bigger than 1? Well, e is around 2.7, and pi is 3.14. So this is actually less than 1. So that means that this form converges, and I can just write this up. I have 4 over 1 minus e over pi. So I can clean that up a little and get that some number, right? That was an easy one. The only thing strange about it was that it was some e and pi and whatever in there, but it looks exactly like that. Let me give you an example of one that we might have to do a little bit more work with. Okay, so this is a bit of a mess, right? So you kind of see there's a 2 and a 3 and a 6 and some powers, but you do have some stuff to the end. So basically what we want to do as much as possible is put this into this kind of form, okay? But in order to do so, I kind of have to mess around with some things here. And of course, as usual, there's various ways to go about. Okay, so what I'm going to do is I'm going to break this one up though, right? Because this is 2 to the 2 and times, 2 to the minus 1. Then I've got 3 to the n here. So this is like 6 over 2. The 2 to the 2n, I can also write as 2 to the 2 to the n, and then here's 3 to the n down here, right? So I did that because what my goal is to figure out what the whole R is. And the whole R is everything that's in power. And here, these both have powers of n to them, but it's not the same. So I want to put everything in together to see what is the same here. So let me see here. I've got 3, and then this looks like 4 to the n over 3 to the n, or this is 4/3 to the n. All right, so I already know I'm out because I've got the 4/3. But to be perfectly correct, let's write it as n minus 1, right? Which means, right, I can always do this as n minus 1 plus 1, or I can pull out a 4/3. So essentially what I want to do, 3 times 4/3 times 4/3 n minus 1. So in fact, my final answer when I kind of massage this into the form AR to the n minus 1 is this guy. A is 4 and R is 4/3. And I know 4/3 is bigger than 1, obviously. So this immediately diverges. That's what I have to figure out. Okay? So it did take me a little bit of mess to do that, but, you know, once you get it straight, it's not too bad. Let me give you another one. Sometimes they, rather than giving you a formula, they'll give you sort of a string of numbers. Okay, so this is one of the examples from the book as well, like it's in the end of the chapter. So you can kind of recognize that this is some kind of geometric series because you've got 9, so 3 squared over 2 squared, and then here's a 3 cubed. Okay, well now maybe I've got 4 squared something, but there's clearly some 4s and 3s and squareds and cubes going on here. So your first guess, a good guess, is that this is a geometric series. Now, it is kind of hard to maybe just look at this and figure out the right form for here just by kind of mentally guessing and checking. Some people can do that, and that's okay. If you can recognize the form and figure out the right A and R, that's fine. However, if it's hard for you, you can't, then what I recommend doing, what I often do just to make sure I'm doing right, is you're going to be comparing terms. So if this is a geometric series, these terms are those, right? So this is telling me that A is 4 and AR is 3. Well, if A is 4 and AR is 3, then that tells me that R is 3/4. Okay, is this making sense though? Because, and it kind of does look like it makes sense, but let's make sure that it goes with the other terms. So AR squared then, just checking that this is right. That's what I'm doing here. Because you could take any two terms and come up with A and R, but it's not going to necessarily tell you that it's right. What if it wasn't a geometric series? In this case it is, but we're going to check. So if I'm going to put these things in, AR squared would be 4 times 3/4 squared. So that's 4 times 9 over 16, or 9/4. That's the right term. And I can do it for the other one too, just to check, make sure if I'm feeling uncomfortable that maybe I got my thing wrong. You see, that actually follows the same pattern, right? Because I've got 27, I've got 64. That cancels out. I have the 27 over 16. So definitely this is a geometric series. These are the right things. So I can go ahead and write this formula like 4 times 3/4 to the n minus 1. And then because 3/4 is less than 1, I'm just going to put it in over here. I got 4 over 1 minus 3/4. So 4 over 1/4. And this whole thing ends up being 16. So it's kind of cute. Okay, I have one more, which is a little bit tricky. So I want to make sure that I do that one. Because what this one has, it's sort of similar to the other one we did, but instead of starting from 1, it starts from 0. So that's a problem, okay? This formula starts from 1. It starts from 1 and it has n minus 1. If you start from 0, this formula should just be r to the n. And that's still right. But if you start from 0 and have n minus 1 up there, it won't work. So my suggestion for you is to stick with the formula that they are using in the book and make it look like that. So what that means, 2 options, okay? One is that you do like kind of what we did in the last problem, which is like write it out and figure out the A and the R that way. So you can do that. So for sure, let's actually really quickly, we can do that. So if I start writing this out, if n equals 0, I have 3, right? Because that's going to be 0. If n equals 1, I have 9 over minus 4. And if n equals 2, I have 27 over 16. Okay, so I can do that and do this equal to A plus AR, blah, 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 and figure it out that way. So this is how you can do it this way if you want. I did want to show you another way, which you'll often see that we do, on the thing that we do in other situations, which is changing the index of summation, okay? So basically we want to walk it from n equals 0 to something that's 1, starting from 1. So I'm going to change my variable so I don't screw it up. So I'm going to let k be n plus 1, okay? Then n is k minus 1. And when n equals 0, k equals 1. So I can change the n to a k. And I have to change it not just down here, but everywhere in the thing. But infinity doesn't change because infinity is infinity whether I'm adding or subtracting 1. Okay? So n equals 0 changes to k equals 1. n plus 1 changes as 3k. And then n equals k minus 1, so that I get this, minus 4 k minus 1. So, rewriting, k equals 1 to infinity. 3 to the k will be 3 to the k minus 1 plus 1 over minus 4 to the k minus 1. So like I have an extra 3, right, like I did in the other case. So this would end up being 3 times negative 3/4 to the k minus 1. And if you did it this way, you would get that too, by the way. Because you can see a is 3, and then AR would be 9 over minus 4. So it would be minus 3/4. So either way is fine. But it is sometimes useful to change indices of summation. In any case, now I see negative 3/4 is between negative 1 and 1, so I just put it into my formula here. A is 3, R is negative 3/4. So this is plus, so what it is 3 over 7/4. So I end up with 12/7. And that's my answer.